All right, let's get right into it. We're going to talk about electromagnetic induction, or EMI. And I know it sounds super complicated, but here's the thing. It's everywhere. I mean, your phone charger, that induction cooktop in the kitchen, even the huge generators that power our cities, they all run on this one single idea.
But let's be real. For most of us, when we study this, the experience is kind of the same, right? We memorize the formulas, we grind through the problems, we get the marks, and we just move on. But do we actually get it? Do we really understand what's happening behind the scenes?
I mean, seriously, why does this feel so abstract? You're told, hey, when magnetic flux changes, an EMF is induced, and it's like someone's casting a spell. Poof, an electric current just appears out of thin air. Well, today, we're going to pull back that curtain and make you actually see what's going on.
Does any of this hit close to home? You can plug numbers into a formula, no problem, but you can't really explain the why behind it. And that negative sign in Lenz's Law, it just feels random, doesn't it? This is totally normal, because we're often taught this like it's a math problem, not a physics concept. So let's fix that, right now.
Okay, first things first. We have to tackle this word flux. Forget the textbook definition for a minute. We're going to use a super simple analogy that's going to make this whole thing click for you.
Okay, so just picture this with me. Imagine that the invisible magnetic field is just like rain falling from the sky. A really strong field? That's a heavy downpour. A weak field? That's just a light drizzle. Got it? This rain is our magnetic field, B. Now imagine you're holding your notebook out in this rain. This notebook, that's our coil of wire, or really any surface. It's got a certain area, we'll call it A. So we have our rain, the field, and our notebook, the area. And you know what? This is where it all makes sense. Think about it. If you hold that notebook perfectly flat, it's going to catch the most rain possible, right? But as you start to tilt it, it catches less and less rain. That, my friends, is magnetic flux. It's just a number that tells you how much rain is actually passing through your notebook.
And this analogy perfectly explains the formula flux, which we call phi, is just the magnetic field strength, B, how hard the rain is falling, times the area, A, how big your notebook is, times the cosine of the angle, theta, which is all about how you're tilting it. See? Maximum rain when it's flat, less rain when it's tilted.
So, here's the most crucial point, and I want you to really let this sink in. Don't overcomplicate it. Magnetic flux is not some mysterious energy. It's just a number. It's a measurement that answers one question. How many field lines are cutting through my surface right now? That's all it is. More lines, higher flux. Fewer lines, lower flux. Simple.
Okay, so we've got flux down. But here's the twist. Just having flux doesn't do anything. A coil of wire can sit in a magnetic field all day long and nothing happens. The real secret, the key to this whole chapter, isn't the flux itself. It's the change in flux.
I absolutely love thinking about it this way. You have to understand, the universe is kind of lazy. It likes things to stay the same. So when you try to change the magnetic flux going through a coil, the coil basically gets annoyed and it fights back. It creates its own voltage, its own current, just to oppose whatever you're doing. It's like a tiny little rebellion.
So how do we start this fight? Well, let's go back to our rain analogy. How could you change the amount of rain hitting your notebook? You could make the rain stronger or weaker. That's changing the magnetic field, B. You could make your notebook bigger or smaller. That's changing the area, A. Or you could just tilt the notebook, and that's changing the angle, theta. Any of these will start the rebellion.
Now let's look at how the coil fights back. This is Lenz's law in a nutshell. If you push a magnet's north pole towards a coil, the flux goes up. The coil goes, whoa, nope, too much, and it creates its own north pole to push your magnet away. But what if you pull the magnet away? The flux goes down, the coil panics. It goes, no, wait, come back, and creates a south pole to try and pull it back in. It's this constant push and pull that drives the current.
So, from now on, when you see a problem asking for the direction of the current, stop guessing. Just use this three-step checklist. 1. Is the flux going up or down? 2. Does the coil need to push or pull to fight that change? And 3. Use your trusty right-hand rule to figure out which way the current needs to flow to make that happen. It's logical, it's simple, and it works every single time.
All right, you've got the concept. You can actually see what's going on in your head. Now, let's translate that into crushing those exam problems. And the good news? They pretty much always fall into just a few predictable types.
You know all those different formulas you have to memorize? Here's the secret. They're all just different costumes for the exact same idea. Voltage is created when you change the flux. That's it. Whether it's a moving rod sweeping out an area or a coil spinning around, it's all the same physics. Your only job is to spot the visual cue, and you'll know exactly which version of the formula to use.
And listen, if you take away one practical tip, let it be this one. This will save you so many silly mistakes. Before you even think about writing down a formula, take 10 seconds and sketch the problem. Draw the field lines, the coil, the direction of movement. Forcing yourself to draw it makes your brain engage with the physics of it all, not just the numbers. Trust me on this.
Okay, I know this has been a lot of information, so how do we actually make it stick? You need a game plan. Here's a simple one-week strategy to take you from feeling confused to feeling totally confident.
Now, the order here is absolutely key. Don't you dare jump into solving problems on day one. Spend the first couple of days just building that mental movie, watching animations. Seriously, play with a magnet if you have one. Once you can see it in your head, then go to the textbook and connect it to the theory. After that, the problems start to feel like puzzles, not chores. And the final test? Try to explain it to a friend. That's when you'll know you've got it.
Okay, let's bring it all home. If you forget everything else from this whole explainer, I just need you to remember these 3 core ideas. They are the foundation of this entire chapter. And that's it. That's the whole story. Flux is just how much. Faraday's law says you have to change it to get a voltage, and Lenz's law says that new voltage will always fight back. Everything else, every single formula, every problem is built on these 3 simple visual ideas.
So I really hope this helped you finally see electromagnetic induction instead of just memorizing it. The real question is, what's next? What other part of physics feels like black magic to you? Let me know what concept we should break down and visualize together in our next explainer.